Last time, I mentioned that I get to teach a linear modeling course at Harvey Mudd College. And I had recently revamped that course so that my students could analyze a real data set from our department library. And previously in the course, I'd given them just a plain old cookie cutter data set, and it really wasn't bringing out the best in them. And so I wanted to challenge them by giving them a project. Well, today I want to share with you some of the frustrations that came up during that process, but also the ways that we worked creatively to address them. Now, one of their frustrations was getting accustomed to the R environment. And for many of my students, this was their first time programming in R. Now, when you're learning to use R on top of your coursework, and you've got a final project that depended heavily on R, well, it really caused a lot of frustration for my students. They had a lot of sleepless nights, and they were frustrated when they got code that didn't run. Well, their hard work and their dedication, it paid off because they got to present their results to the library staff. And some of their analysis, it was done so well that the library decided to implement their model. And I wish you could have been there to see their faces, to see their hard work pay off when they got to present the work that they'd done and analyze this huge data set in R. And in talking with them afterwards, there was just a sense of accomplishment, of pushing past their limits and accomplishing more than they really believed they were capable of. And so that's my goal for you in this course. I want you to push past your limits. Maybe you have challenges with R, but I want to push you to push past that. But let me tell you how we reached that point. Now, a major challenge that my students struggle with was tackling real data. And so the data sets that we analyzed in R, well, these have already been cleaned. The ones that we're doing in this course, there's no missing values, there's no incorrect entries, there's not a lot of outliers in those data sets. But by contrast, this library data that my students had, it was a mess. I mean, we spent well over a week writing our code just to parse the data. I mean, we just had to get it in a usable format for us to do the statistical analysis on. And so by the time we finally arrived at a clean and accurate data set, it didn't even satisfy any of our linear model assumptions. I mean, what do you do when you're taking a course that's called Statistical Linear Models, and you end up with a final project, and your data set doesn't satisfy any of your assumptions for linear modeling? All right, well, don't panic. There is an answer. And so our solution was to transform the data. Now, when we transform the response variable, this can help us in a lot of ways. First, it can help us eliminate heteroscedasticity. So that's increasing or decreasing variance in our data. And it can also help our data satisfy the assumptions of normality, so our residuals need to be normal, independence of the residual, and then linearity. Now, here's a sampling of the types of transformations that my students were able to use for their final project data. And hopefully you'll be able to use some of these transformations as well as you start to work with your own data. Now, this first data set, it has an exponential shape, and it clearly doesn't satisfy the assumption of linearity. Notice that you see huge variation by time of day, and your residuals, they're large in magnitude, they're not centered at zero, and they're definitely not balanced. So these are heteroscedastic and have an increasing variance. You can look and see your histogram, which is slowly also skewed to the right. Now, along comes the natural log, and look what it does to this data set. After just taking the natural log, our data appear linear, and our residuals, they even look more linear. Notice how they're centered at zero, they have much less of a pattern, And you see where our histogram has even shifted closer toward normality. Now, this data set likewise has a curved pattern. Notice that there's non-constant variance as well and non-normal residuals. And so in this case, the way that we solved the problem with this data was by taking a square root transformation. And so that got us to normality, as you see here, both in the original data set and also in the residuals. Now here's another data set where the original data is curved, and notice now the residuals have a decreasing variance. So still heteroscedastic, but the variance is decreasing. And this histogram is skewed to the left. Now for this data, an exponential function was the best transformation. It helped to eliminate the nonlinearity, and it gave us normal residuals. And now here's a slightly different data set with a curved pattern. Now you'll notice that these residuals have a pretty clear pattern, and the histogram is heavily skewed to the left. Now in this case, our solution was to take the square of the data. And notice what a great job that did in transforming us and helping us to satisfy those model assumptions. All right, let's revisit the simple regression setting. We've got those population parameters, our beta naught parameter for the slope, and beta 1 for our y-intercept. And so in order to estimate our population parameters, we're going to collect a sample, and we're going to solve for our beta naught hat and beta 1 hat. But here's the question. How much do our estimates depend on the particular random sample that we happen to observe? I mean, if we had 2 random samples and we calculated 2 beta naught hats and 2 beta 1 hats, how different would they be? Would our estimates be much variable from sample to sample? And how would that variation change as the sample size increased or even decreased? Now remember, we're ultimately interested in drawing conclusions about our population, not about a particular sample that we observed. So how confident can we be that our sample estimates accurately reflect the population parameters? All right, here's an example. Now this blue line that you see here, it represents our true underlying population. Now let's sample 5 points from this population, and we're going to fit a regression line to those 5 points. Now you'll notice sometimes our 5 points, they do a nice job of estimating the population slope. But it's difficult to precisely estimate the slope with so few points. On the other hand, what if we use 50 data points? We sample that from the population. Notice the difference in our regression line fits here. So even though there's variability in the sample, because we have a larger number of points, we're able to more accurately estimate the true population slope. Now, hopefully it's becoming clear that our parameter estimates, our beta 1 hat and beta naught hat, they're actually random variables, right? Their estimates change from sample to sample. So then the question becomes, well, if they're a random variable, that means they have to have some underlying distribution. What do you think it is? All right, I'll give you this one. It's the sampling distribution of beta naught hat and beta 1 hat are normal. And actually the proof of that statement is not very interesting. Basically, you can write both beta naught hat and beta 1 hat as the sum of normal random variables, which in turn makes them normal. But what is interesting is that the mean of beta 1 hat is equal to the population mean. In other words, it's unbiased. When I take the expected value of beta 1 hat, I get right back to my true population parameter. And the way I estimate the sample standard deviation is S of beta 1 hat equals my sample standard deviation over the square root of the sum of xi minus x bar quantity squared. All right, so let's unpack this. First, beta 1 hat is unbiased. Now, this is a key property that we like in our estimates because what? We know that tells us that on average, our estimate is going to approach the true population parameter. Secondly, the standard deviation of beta 1 hat. Now, ideally, we want the standard deviation of beta 1 hat to be small. So in that case, this would give us a tighter fit of the line to our data. And so the standard deviation is going to be small when our denominator is large. Notice that denominator, that's the sum of xi minus x bar quantity squared. So in other words, if we only have a few points, right? If we've got a small number of points, or even if our data is clustered, then our standard deviation for beta 1 hat is going to be large. Whereas if we've got a larger data set and if we've got values that are much more spread out, like we saw in our example, we're actually going to get a more precise estimate of the slope. So think about that. If I've got data values that are close together and clustered, then it's going to be hard for me to try to fit a regression line to that data, right? So I don't really have any way to ground it. But once I get data that's much more spread out, then I can easily fit a regression line to that data, right? My slope line is going to be a lot tighter when I do that. Now, what's even more interesting is that we can now test whether our estimates are significant. All right, here's what I mean. Here's an example of a linear regression fit where both the slope and the y-intercept estimates are significant. Notice that our data lies close enough to the y-axis that we can extrapolate out to y equal to 0 fairly accurately. And in spite of the variability in our data, we can fit a regression line that has a non-zero slope. Now check out this data. There's no relationship between x and y. So here our slope estimate is just going to be equal to 0. But notice we can still estimate the y-intercept, and that would just be the constant at y bar. So our model for this data would be a straight line centered at the mean y bar. Now here's an example where we have a linear trend in the data, so we can accurately fit beta 1 hat. But notice, look at that x-axis, and notice the range of your x variable. Now we're quite a ways out from the y-intercept line. So imagine if you had to try to extrapolate that regression line all the way out to where x equals 0. Well, there's going to give you so much uncertainty in your y-intercept that you're really not going to be able to accurately estimate it. So it would be insignificant. And we all know that extrapolation is one of the 3 deadly statistical sins. So while in this case we have a significant slope estimate, our y-intercept estimate, it wouldn't be significant. Now, we use confidence intervals and hypothesis tests. That's the way we learn about our population parameters. And we can actually calculate those for our beta 1. Let's do that now. So here's the null hypothesis. H naught, the null, is that beta 1 is equal to 0. Right? So in other words, that would imply that there's no linear effect. So we would just ignore x. There's no relationship between x and y. Right? That's our null hypothesis. And so we want our data to come along and give us enough evidence to reject that null hypothesis in favor of the alternative. So our alternative hypothesis is that beta 1 is either greater than 0 if we have a positive slope, or less than 0, or we could even just test that it's not equal to 0. Either of those implies that x and y have a linear relationship. And our estimated slope in that case is going to be beta 1 hat. Now, our test statistic is going to come from the t distribution. Right? Notice we're using t and not z. Now, why is that, do you think? Now, remember, the t distribution helps us when we're estimating more things in our statistic, right? If we're drawing more information out of our sample to come up with our test statistic. So notice in this case, there are 2 places where we're using our sample to estimate values in our test statistic. So first is beta 1 hat, and also the standard deviation of beta 1 hat. So our test statistic follows a t distribution, beta 1 hat minus 0, so that's the mean assumed under the null, divided by its standard deviation. Now, this test statistic has a t-distribution with n minus 2 degrees of freedom if the null hypothesis is true. Now, we can also calculate our confidence intervals. So that's our beta 1 hat plus or minus our t critical value. So this is t at alpha over 2 and n minus 2 degrees of freedom times the standard deviation of beta 1 hat. Now, the confidence interval for beta 1, that's going to give us a range of values where the true unknown parameter is likely to reside. So that's the benefit of calculating a confidence interval. It's also going to answer the question of, is y related to x? So if our confidence interval for beta 1 actually contains 0, then that tells us that there's no linear relationship between x and y. Whereas if it doesn't contain 0, well, then that gives us evidence that there's a linear relationship between x and y. Let's do an example in R with the Motor Trends road test. Now, the following data was extracted from the 1974 Motor Trend magazine. And what it has is fuel consumption as our y variable and 10 other aspects of automobile design and performance. So these are our predictors, our x's, for 32 automobiles from 1973 to 1974 models. And so we're going to explore this data set. It's called MT-CARS, and we're going to use linear regression to see if we can predict vehicle gas mileage based on the vehicle weight. Now first, let's look at a summary of the data. Here we can load the data with our library command, so library of data sets. And the data that we're pulling up is MT-CARS. So a summary statistic shows that you've got things like the mile per gallon, the weight, the horsepower, the cylinders. Notice that your miles per gallon range from a minimum of 10.4 to a maximum of 33.9. Now, a scatter plot of weight versus miles per gallon is going to give us a sense of the data. Notice here we've plotted MPG, or miles per gallon, with a tilde of weight. And we're telling R that this data comes from MT-CARS. So the first thing we want to do when we're thinking about doing a linear regression or a multiple linear regression is to model the data. Right? We want to see visually, does a linear relationship first exist between those two variables? And here we see that there clearly is one. Now, this scatter plot shows a roughly linear relationship between weight and miles per gallon. And so it's suggesting that, hey, a linear regression model, it might work here. Because think about it, as the weight of a car increases, well, we would expect the miles per gallon to decrease. All right, let's fit a linear model to our data. And here's how we do that in R. I'm going to call that MPG underscore model, so miles per gallon model. And it's equal to a linear model of MPG tilde weight, where data equals MT-CARS. And then I'm going to use my summary statistics. So summary of MPG model is going to give me the results of that model. Notice here, so R gives us our residuals, the range of our residuals from the minimum to the maximum, and also the median. So this is a quick way for you to get an idea to see if your residuals are roughly normally distributed. So you want to look at that median and see if it's somewhere close to 0, and make sure you don't have really large outliers in your maximum and min. Now check out the coefficients for that model. Here you see that we've estimated the y-intercept at 37.2, and we've estimated our slope of minus 5.3. Notice also R gives you the standard error, so 1.8 for the y-intercept and 0.55 for the slope. You also get your t-statistic, so that's calculated from your sample, and then that last column, that's your p-value. Right? So notice R is already testing every time whether or not our slope and our y-intercept are significant. So this output shows us the formula that we use to make the model. Again, it gives us that 5-number summary of the residuals, and it gives us those coefficients. So these are the constants that are going to be used to create the best fit line. In this case, you saw that our y-intercept was 37.28 and our weight slope was minus 5.3. Here's our model for that regression line. It would be miles per gallon equals 37.2851 minus 5.3445 times the weight. Now, again, the t-value and the p-value columns, that indicates the result of a t-test. So this is checking whether or not the coefficients chosen are going to differ significantly from 0. And now the intercept estimate, the beta naught hat, this is significant with a p-value of pretty much equal to 0. And likewise, you see that our slope estimate has a p-value also of approximately 0. Now at the bottom of the summary output, we see the values of interest to us are going to be the multiple r squared and the adjusted r squared. Now the multiple r squared, this tells us how much of the variation in miles per gallon can actually be explained by weight. And the adjusted r squared, well, this is a modification of our normal r squared, and it adjusts the model because, if you have multiple independent predictors or variables, it's going to penalize you for that. In fact, as you add more predictors to your model, your normal r squared reading, it can only increase, even if those predictors aren't significant. So in general, we'd like to keep models as simple as possible. So the adjusted r squared is preferable. So that's how we're going to assess the explanatory power of our model. Now in this case, roughly 75% of the variation in miles per gallon is explained by a model with the weight. Now we can also calculate a 95% confidence interval for our true population slope. And we can do this using the QT command. So that stands for quantiles of the t distribution. Now here we're plugging in 0.975 as our alpha parameter with the degrees of freedom equal to 28. And so that gives us our quantile estimate. So this is going to be the critical value that we compare it to of 2.048. We're 95% confident that the true slope regressing miles per gallon on weight is between negative 4.1 and negative 6.4 miles per gallon per 1,000 pounds. So here you see the estimates and the standard errors that go into that model. We can also do a hypothesis test for beta 1. So is the slope significantly different from 0? All right, let's calculate our sample t-test statistic, and we can actually compare that to the critical value that we just got. All right, our t-test statistic is beta 1 hat divided by its standard deviation, S of beta 1 hat. In this case, we saw that beta 1 hat was minus 5.3 approximately, divided by that standard deviation, 0.5591, to give us a t-test statistic of negative 9.55. So we'd compare the absolute value of that t-test statistic to that quantile of the t distribution that we calculated, 2.048. And notice, since our absolute value of t is greater than our critical value, we reject the null hypothesis that the slope is equal to 0. Now we can also do hypothesis testing with p-values. We can confirm the p-value reported with the following code. Now here we're using PT. This is giving us the percentile of the t distribution, because remember, your p-value is evaluated at your critical value that you've calculated from your data. So in this case, our PT is evaluated at our minus 9.559 with 28 degrees of freedom. And notice how we get that p-value of 1.29 times 10 to the minus 10, and see how it matches up to exactly what R got. Now, if we computed this p-value at an alpha of 0.05 or an alpha of 0.01, in both cases, it would lead us to reject the null hypothesis that beta 1 was equal to 0. Now, we have to verify our model assumptions, and those mostly have to do with the residuals. So here's a histogram of the residuals from our model fit. They don't look too shabby. They're sort of centered, but you've got a little bit of skewness there. Now we can get a normal QQ plot of those residuals just to get a better idea of their shape and to visually confirm normality. Notice here in R, we've just done a QQ norm of the residuals left over from our model, and we fit a QQ line to that. Now, actually, our residuals do a pretty nice job of staying fairly close to that normal line. But we do see in the tail ends where we tend to veer away. And so if I see this kind of plot, you know what it's going to lead me to do next. Shapiro-Wilk, right? We can never really estimate a QQ plot just by looking at it visually. Notice that our residuals are normal, right? Our Shapiro-Wilk test, Shapiro.test, evaluated on our residuals, returns us a p-value of 0.1044. Now, clearly, we need to add more predictors to our model. But we're going to run into a pitfall when we do this. And that pitfall is called collinearity. Now, collinearity occurs when you have two or more predictors that are closely related to one another, or they're highly correlated. Now, the presence of collinearity, it can create problems in the regression context because it's difficult to separate out the individual effect of collinear variables on the response. So because sometimes your responses are correlated, it's hard to see which one of those variables are necessary in predicting your Y. But it's fixable. In fact, in the next lecture, we're going to dig into multiple linear regression. And we're going to tackle this issue of collinearity by examining the correlation matrix of our predictors.